Hello, and welcome to the 18th lecture. We're going to talk some more about the closed interval method, and then we're going to start a new topic, which is the mean value theorem. So, where did we leave off? We got to the point of defining critical numbers. And for a given function, C is a critical number if either f prime of C equals 0 or the derivative does not exist. Okay, so if we draw a graph, and let's say this is A and this is B, and we have some function that maybe does something like this, something like this, like this, okay? Let's identify all the critical numbers. So there seems to be one here, right? So a critical number, the derivative is 0, that's equivalent to the tangent line being horizontal, so there's one here. C1, there's another one here, C2, there's one here, C3, here we have a peak, it's not differentiable, it's not locally well approximated by a tangent line, that's C4, another one here, C5, another one here, C6. And the point of this is that there's a very important relationship between local maxima and local minima and critical numbers. And the relationship is what we can see here on this graph. We see that whenever we have a local maxima, such as here, it must live above a critical number. Yeah? A local minima must live above a critical number. This local maxima, where we have a peak, also lives above a critical number. This local minima is again above a critical number, and so is this one. Yeah? But note, it is not the case that above every critical number there is either a local max or a local min. Because as we see here in C2, we have a critical number which is not a local maxima or a local minima. And the example which we discussed before is x to the 3 and f prime of 0 equals 0, but no local max at 0, right? So it's an only one-way relationship, right? We know that if we have a local max or local min, then it must live above a critical number, but not the reverse. Not that above every critical number there is a local max or local min, right? But this one-way relationship is good enough for us because what we do is we use this to find the absolute max using the basic fact that the absolute max will either be at the endpoints, okay, and we can just check what those values are. We can just plug in f of A, f of B, or it'll live somewhere in between. If it's somewhere in between, then it has to be a local max, and therefore it's going to live above a critical number. So we can stick in the values f of A, f of B, and then f of all of these guys, and amongst those guys, the biggest number must be the absolute max, okay? So if you're comfortable with what a critical number is, and you make this basic observation that either the absolute max is at the endpoints or it's inside and therefore it's also a local max, then this entire algorithm makes a lot of sense. You know? And to find the absolute min, it's exactly the same, right? We're going to compare the endpoints, compare the values at all the critical numbers, find the smallest value, that will be the absolute min. So that is the closed interval method, and now we're going to practice it, and the first thing to learn to do is to find the critical numbers. So let's do our first example. This is example 7. find the critical numbers of, firstly, this function, and secondly, this function. It's a 5 here. Okay. All right, let's do this. Solution. So the first one is just a polynomial, so it's differentiable everywhere. So there's no issue about critical numbers that are non-differential. They're all differentiable. It's differentiable everywhere. So the only ones that we can find that will exist for this function will be where the derivative is 0. So we just calculate the derivative. Okay, so the derivative is 0. Only happens when x equals 2 and when x equals 0. And that's it. All right, cool. Now the second one is a bit more tricky because this is not a polynomial because of this root power here. Okay, so a brief recall about root powers. So as I've said a number of times, at this level, you've got to be able to visualize elementary functions very, very easily. It shouldn't be a difficult thing. And what you should know at this point is that the square root function looks like this, right? In particular, it's above the line y equals x, which is not a surprise, because if you take, for example, 1 over 4, yeah, there's 1 over 4 right here, then the square root of 1 over 4 is 1 over 2, right? Because 1 over 2 times 1 over 2 is 1 over 4. So the square root of it is up here at 1 over 2. So it is much bigger, right? If we do, say, 1 over 100, which is like over here, yeah? The square root of 1 over 100 is 1 over 10, which let's say is, so my picture's not very realistic, is over here. So 1 over 10 is much, much bigger than 1 over 100, yeah? So the square root function curves in like this, you know, just from observing what square roots do to numbers between 0 and 1. And if we calculate the derivative, we find actually the derivative has this increasingly big value as we approach 0, and at 0 the derivative doesn't exist because it's got to be infinite. But that's true for any root function, right? So for any alpha which is between 0 and 1, then f of x equals x to the alpha looks a lot like this. In particular, it curves down like this. Between 0 and 1, it's always going to be bigger than x itself. And if we calculate the derivative, what do we have? We have alpha x to the alpha minus 1. So it blows up as x approaches 0, which is what we see from the picture anyway. Right? The reason I say that is because before you do any calculation, when you see something like this, I want you to have some idea what it looks like. Okay? Now, around 0, this 4 minus x part is benign. It's not doing anything interesting. It's just like the value 4, right? But around 0, this thing is doing something pretty interesting because this thing is curving down like this because it's the root function, right? So we would expect this thing to go to 0 in a kind of way analogous to this. Yeah? Just from the pictures, we would expect that kind of behavior, right? And that should give us a warning that at 0 we have a point which is not going to be differentiable. So before you start the calculation, try and visualize and understand what you might expect to happen. In this case, it's such a simple calculation we didn't bother, but in this case, we do spend a second to think about it. All right, with this in mind, let's do the calculation. Let's see what we get. So f prime of x. It's the product rule. We're differentiating the first term, leave the second term alone. So you have 3 over 5, x to the minus 2 over 5, 4 minus x. Leave the first term alone, x to the 3 over 5. And then if we differentiate the second term, we just get minus 1. So we're going to have minus x right here. Okay. So I'd rather have this under the same denominator, right? So the denominator of the first term is x to the 2 over 5. So what I'm going to do is I'm going to multiply this guy by 1, and 1 will be able to form x to the 2 over 5 divided by x to the 2 over 5, right? So on the top, then I'll have x to the power 1. On the bottom, I'll have x to the 2 over 5, right? So if I do that, I get this. I get 3 over 5, 4 minus x minus x itself over x to the 2 over 5. Okay, and I want to make that even a little bit neater, so I'm going to multiply top and bottom by 5. 3, 4 minus x minus 5x over 5x to the 2 over 5. Like this, and then let's see what we get. We're going to have 12 minus 3x minus 5x, and that's going to be 12 minus 8x over 5x to 2 over 5. And we can factor out a 4 here, so we're going to have 4, 3 minus 2x over 5x to the 2 over 5. Okay, so if we look at this, we see that straight away there's going to be a 0 derivative when we let x be 3 over 2, right? When x is 3 over 2, this thing on the bottom is non-zero, so we see that and what do we see? We see that when we let x approach 0, for example, if we let x approach 0 from the right-hand side, then on the top here we're just going to have 12, and on the bottom here we'll have an incredibly small positive number. So the limit as x goes to 0 of prime of x is equal to 0, is equal to infinity. And in particular, the derivative at 0 does not exist. Yeah? So 0 is a critical number. And those are the only two critical numbers. So the top will only be 0 if the bottom is non-zero when x is equal to 3 over 2. And when x equals 0 on the bottom, then again the derivative doesn't exist, so that's a critical number. So those are the only things that will be a critical number. Away from 0, this thing is fine. If the derivative exists, we have no problem. Okay, so 3 over 2, 0, the correct numbers. And that's it. That does this. Okay, so it is just applying differentiation. Now, once we have this ability to find critical numbers, then we can actually find the absolute max and the absolute min of whatever function we're given, continuous function we're given on a closed interval. So let's do the next example. Example. Find the absolute max and min of this function. F of x equals x to the power 3 minus 3x squared plus 1 over this interval minus 1 over 2 less than x less than 4. Okay, let's see. All right, so solution. This guy is a perfectly nice differentiable function, so the critical numbers are only where the derivative is 0, so let's just calculate the derivative. And we did this, actually, this one before. Yep. X equals 0, x equals 0, or x is equal to 2. And let's call that step 1. Okay. Now that we found the critical numbers, we're going to plug those critical numbers into our function, and we're also going to plug in the endpoints, and we're going to see what we get. So f of 0 is easy. It's just going to be 1. F of 2, what are we going to get? We're going to get 8 minus 12 plus 1. So 8 minus 12 is minus 4 plus 1, so it's minus 3. You know? And what about the endpoints? F of minus 1 over 2. What do we have? We're going to have minus an 8 here, and then here we're going to get minus 3 over 4, and then here we're going to have plus 1. So we can write this as minus 1 over 8, minus 6 over 8, plus 8 over 8, and that's just going to be 1 over 8. Okay, so that's that critical number. And the other critical, no, sorry, that is that endpoint. And the other endpoint is when we have f is 4. F of 4, what do we have? We have 16 times, start again. We have 4 to the power 3, which is 16 times 4. So let's write that. And then we have 3 times 16. And then we have plus 1. So we're going to have just 17, right? We just have 17. That's it. All right, so we have just 2 critical numbers, those guys. We have 2 endpoints. We just have 4 numbers to compare. So we're going to find the biggest number from this list. And the biggest number is 17. So the absolute max and absolute min is minus 3. And that's it. So the computations are pretty easy, right? Simply getting the algorithm right is the main thing you have to learn. And again, you will get it right if you understand why it works. And why it works is rather basic. It's rather straightforward. Just a logical observation that a local min, not again an absolute min or an absolute max, if it doesn't live at the endpoints, has to live somewhere in the center. So it's also a local max and a local min, so it lives above a critical number. If you have that clear in your mind, if you can see those pictures, and the pictures are not hard, right? So you'll need to think of is this picture. This picture where the absolute max is at the endpoint, and then this picture where the absolute max is in the interior. If you have those 2 pictures as the main 2 logical possibilities you can have, then you're golden, right? Then you can do this, because you're going to find this value at this critical number, and you're going to find this value because you're going to check out the endpoints, and that's it. All right, so we will practice this on the practice exam, and you'll have obviously WebAssign homeworks and practice WebAssign homeworks doing this, but this shouldn't be a difficult topic. This should be a rather straightforward topic. So please get good at this and feel confident with it, and that's the entire section. So we're going to erase the board, move on to a new section where we discuss a new topic. So our next topic is the mean value theorem. And we're going to start by introducing a kind of a baby version of it, which is called Rolle's theorem. And Rolle's theorem is the following. So, given a continuous function on the interval AB with f of A equaling f of B, and f is differentiable on this open interval, and f of A equals f of B, then there must exist some C in this open interval AB such that f prime of C equals 0. Okay, so as always, theorems will become clear once we draw a picture. But the best way to do this, if you are watching this video and you weren't in person in class already doing this with me, is to pause the video right now and to draw a picture to represent these hypotheses, and then from that picture show why there must exist points C such that f prime of C equals 0, and identify the points on your picture on the x-axis where you see that happening. Okay, so once again, the way we're going to see this is that we're going to draw a function, a typical example of a function satisfying these hypotheses, which means these assumptions. So we're going to take a continuous function, okay, on this interval where f of A equals f of B, right? And it's differentiable on the open interval. Okay, oh, I've written that assumption twice. Okay, it's a bit of overkill. And we are going to draw such a function, and we're going to identify the points where we see that f prime is equal to 0. Okay, and you should be able to see that once you draw a few pictures. Right? So pause the video, do that, draw your diagram, and then play it again, and you'll see me draw this. All right, so let me not have the same thing written twice out of a kind of feeling of neatness. Let's draw the picture. So this is how we can understand basically all the theorems. We draw an example of something that satisfies these hypotheses. So these are A, this is B. Let's say this here is f of A, f of B takes the same value, and then the only hypothesis is that it's continuous, okay, and it's differentiable, so it's some kind of thing that does this. That would be an example, right? Sure enough, we see there are points where the derivative is 0, because right here and right here, this is where the tangent line is horizontal, and therefore the derivative is 0. Those things are equivalent. So our points would be here, C1, C2, C3. And no matter what type of function, no matter what example we draw, we'll always see points like this, right? Because if we start going up, then the only way we get back down to f of b is if there is some point where it stops going up and starts going down. And when it does that, we're going to have a point where the derivative is 0. Yeah? Okay, so another metaphor for this is suppose that f represents your position, right? And a to b is some time interval. Then f of a is where you start, and f of b is where you end, right? Which is exactly the same place. And f prime again is your velocity. So let's imagine I am the thing which is moving, and over with respect to time, and my position is given by f of t, right, between a and b, right? So here I am at f of a, and if I start moving forward, I'm moving forward, I'm moving forward, I'm moving forward. Yeah. If I keep moving forward, and my velocity is always positive, then I'm never going to be able to get back to where I started at time b, right? So at some point, I have to have velocity. I have to slow down and stop and start going backwards, right? So when I stop, I have velocity 0, which is f prime of c equals 0. So here I'm stopped, here's a point, and then I go backwards, and maybe I go backwards, and then at time b, I'm exactly where I started, or maybe I go backwards, and then I go forwards again, and then I stop again, and I go backwards again, and then there's a couple of points, actually 3 points, where I stop and have 0 velocity, yeah? It's clearly got to be the case that there is some point where the derivative is 0, and this metaphor of moving, where my position is given with respect to f, and this graph, which has its slope given by its derivative, and thinking about it has to, if it increases, then eventually it has to stop increasing and go down. These are exactly the same things, right? These are exactly the same things, just said in a different way, right? So we believe this theorem is definitely true, and this allows us to answer some concrete questions. So here is a nice example. Prove that x to the 3 plus x minus 1 equals 0 has exactly one real root. Okay, so this might seem like it's got nothing to do with Rolle's theorem to begin with, okay? But obviously it does, because otherwise we wouldn't have it right here, yeah? So let's try and think about it. If we define this function f of x to be equal to this quantity, right? So f has a root, or f of x equals 0 is exactly the same as saying that this equation has a root. So the same as x is a root. Okay, and later we're going to learn how to sketch things like this, but for the time being, let's not think about it too deeply. Let's just think about what kind of picture we have, right? Let's just put some kind of picture there, and then see the consequences. And what we're going to do at this point is we're going to do something called arguing by contradiction. Okay, so we're told prove that this has exactly one real root, yeah, and we're going to assume that that's false, and therefore it has more than one root. So argue. So this is a standard phrase in math, argue by contradiction. Many of you maybe have never seen this before, but it's a very useful and a very common thing to do. So argue by contradiction. Okay. Assume f has more than one root. Okay, and now we draw a picture of this guy, which, with that assumption that it has more than one root, without really knowing what it looks like, but just to give us some visualization, right? So it's a kind of a cubic, so we expect it to go up, down, and then down, or vice versa. So let's say it does something like this. Yeah? Again, it doesn't really matter. We're just putting this here to concretize the situation and relate it to Rolle's theorem. All right, so if we look at that, what do we see? Well, we see that obviously this is a continuous and differentiable function, so it satisfies the hypotheses of Rolle's theorem. And the assumption we made by contradiction was that we had more than one root, so that we have points like this, like this, like this, as opposed to just having one point. Now, if we have this kind of stuff, then what does that mean? Well, it means that if we just look at one of these intervals, for example, from here to here, let's call this thing A and this thing B, then our function, right, has this property that f of A equals f of B, which is equal to 0, yeah? Because A and B are roots, right, and there's more than one, right? So between A and B, we satisfy all the hypotheses of Rolle's theorem. So we can apply Rolle theorem to f on this closed interval A to B. Yeah? And if we do, then there must exist some critical number, some point here, C, such that f prime of C equals 0. Yeah? That is also a critical number, but let's not use that notation in this section. Right? So now we have some idea what would be useful to do. We see that Rolle's theorem says there should be some derivative between A and B, which is derivative of 0. Now let's calculate the derivative. Yeah? No, we don't calculate until we have some idea why we're doing it. And we're doing it because we expect something about the derivative should be true between some arbitrary interval or some specific interval with a, b, where a and b are the roots. So if we calculate the derivative, we have f prime x is equal to 3x squared plus 1, right? And that thing, no matter what value of x, is always greater than or equal to 1, right? And this is a contradiction because we started with the assumption that there's more than one root, okay? We have that for these roots a and b, okay, we can apply Rolle's theorem, you know? So by Rolle's theorem, we have the f prime of c equals 0 for some c in the interval a, b. However, we've also just calculated the derivative is always bigger than or equal to 1 everywhere, which includes everything between a and b. So that's a contradiction. We can't have both of things true. We cannot have the derivative is always bigger than or equal to 1 and there is some c between a and b where it's 0. Yeah? So the only way the universe can continue is if we are wrong about our starting assumption. Our starting assumption that we have more than one root is not true. Yeah? It's not true. Yeah? And that's called an argument by contradiction, and it's a simple example of what's so. So let's call this thing here star. So star cannot be true. We call this, we write contradiction. And therefore, the initial assumption, which, let me underline it, this is the initial assumption, is false. Okay. In fact, now that we've done this calculation, we can think a bit more about this. If this guy has got derivative always greater than equal to 1, it's actually always increasing, right? And if we let x be incredibly negative, then this term will dominate, so it'll be towards negative infinity. And if x is incredibly positive, then it's towards positive infinity. And since it's always increasing, then what's the graph got to do? It's just got to go, it's got to be increasing, increasing. It's got to cross through the x-axis just one time. So just from what we know about slopes of functions and just elementary observations about this thing, it's actually not a surprise there's just one root. We didn't have to use Rolle's theorem, but we could use Rolle's theorem, and we just did, and that gave us the same answer, right? Cool. All right, so that is the first simple application of these ideas. And now we're going to talk about the mean value theorem, which is a more general version of Rolle's theorem, and it is going to make sense to you in a very similar way. Okay, so mean value theorem. Mean value theorem is so important, it's abbreviated to MVT. So the hypotheses are very similar. So f is continuous on AB and differentiable on the open interval AB, okay. Then there exists C in AB such that f prime of C is equal to f of B minus f of A over B minus A. Okay. Again, the best thing to do now, if you're watching this on video and you weren't in my class today, is to stop the video and draw a picture of a function that satisfies these hypotheses, okay? And then show on your picture where there exist these points C in AB such that this is true. And the hint is to look at this number here and ask yourself, what is this number? Where have we seen this kind of thing before? What is its geometrical meaning, okay? And I claim that if you succeeded with the Rolle's theorem and you were able to find point C when you drew things like a picture like this, if you think hard enough, you will also succeed with this, okay? So please do that, draw the picture, give it a few minutes, give it a good go, and then once you think you have the picture, or once you're sure you can't come up with it, then play the video again and watch what I do. Okay, so let's draw a picture. So the difference between Rolle's theorem and the mean value theorem is that we don't have this assumption that f of A equals f of B, right? So if we are here at f of A, and suppose we are here at f of B, okay, then what does the function do? It's gonna go up and then go down and then go up and then go down and then maybe go down like this. Yeah? And let's think about what this thing here represents. What is this quantity? Well, what is f of B minus f of A? Well, f of B minus f of A is going to be this distance, right? Yeah? And what is B minus A? It is this distance. Yeah? So if we draw the line connecting this point here, right? So to completely nail this down, let's put in these things as coordinates. So let's write A f of a, do it again. A f of a, and this thing is b f of b. Then this is the secant line connecting these 2 points, right? And this quantity is the slope of the secant line because it's how far up or down we go divided by how far along. Yeah? Cool. So, why is the theorem true? Well, f prime of c equals this quantity is exactly the same as saying that the slope of the tangent line at the point c, f of c, is going to be equal to f prime of c, which is the same as the slope of the secant line, right? So what we're looking for is points c between a and b, such that when we look at c, f of c, and we take the tangent line, that thing will be parallel to the secant line, yeah? So imagine moving this line up and down until you touch parts of the graph, right? Yeah? And when you touch a point of the graph, you will see that what you've got there is a tangent line, yeah? So for example, right here, the tangent line to the point right here is parallel to the secant line. So this guy here, C, and this point on the graph with coordinates C, f of C, that's a point for which f prime of C is equal to this quantity, yeah? And it's also true here, and it's also true here, and it's also true here, so we have a whole bunch of them, yeah? And if f of a was equal to f of b, then what we would have would be that this number here would be 0, and we'd be looking for points for which f prime is equal to 0, and we're exactly in this position, in this situation again. And so we see that Rolle's theorem is just a special case of this thing, the mean value theorem. You know? Rolle's theorem is a good warm-up because it's perhaps easier to see this rather than jumping in straight to this thing. Okay, so this will have useful implications for us. Let's think about f as position, and let's think of the x-axis as time, right? So what is this quantity? Well, this is where we got to at time b minus where we got to it where we were at time a. So this is how far we've traveled, right? F of b minus f of a is how far we've traveled, and b minus a is how long it took us, right? So this is the average velocity over the time interval a to b. So let me write that down. If f is position, then f of b minus f of a over b minus a is average velocity. Over time interval a to b, all right? Cool. So what is this saying? It says that if we are moving with this particle f, then at least one point, if not, but perhaps many more, the particle has to have velocity equal to its average velocity. And again, this makes intuitive sense to us, right? So if we start from here, time a, and then at time b, I'm over there at the end, right? Then if I'm always going faster than the average velocity, then I will arrive at time b, well, I will arrive, by time b, I will be actually further than where I'm supposed to be, right? If I'm going faster than the average velocity, right? So if I'm starting off faster than the average velocity, then eventually I'm going to have to slow down and go slower than the average velocity in order for it to be true that at time b, I am at f of b. Yeah? Make a concrete metaphor. Imagine for simplicity that between Dayton and Ohio, it's 100 miles. And you have a nephew or a niece who left from Dayton at 3 p.m. and arrived at your house at 4 p.m. And you're a bit concerned. You go, hey, nephew or niece, I think you're going a bit fast there. Your average velocity was 100 miles an hour. You must have at least at some moment in time be going 100 miles an hour. And they go, no, that's not true. I was under the speed limit. And you can go, well, the mean value theorem says, no, you actually must have been going 100 miles an hour at least at some moment in time. You know? And that's definitely true. It's definitely true. It's a theorem. So you can appropriately caution your younger niece and nephew about speeding on the journey with the power of calculus. All right, so we will use this later with some other applications. We'll get used to the power of mean value theorem, but that's it for today. So have a good day.